Swayam Prabha. Digital India. Educated India.
So, coastal process modeling. So, the foreign faculty is Professor Zhang Kang. She has flown and reached Chennai only in the morning, and she is coastal engineering, teaching water and coastal engineering from Griffith University. Griffith University has, she will give introduction, but a few campuses. She is from Gold Coast campus, Brisbane, and I think they have also a digital and other places, also few other places, and where she has been teaching the coastal. And of course, I have a very long-standing association with Dr. Hong. Is that we started our career at Singapore together, National University of Singapore, and I was working in the wave modeling. She has been working in the hydrodynamic modeling, and of course, I am following or continuing the same wave modeling for many years also. I think more than 2 decades or third decades I am working. She has been also continuing with the hydrodynamic modeling, and with coastal engineering she is an expert in that particular region, particularly on the Gold Coast and other places, and many of you may be knowing that Gold Coast has a very beautiful beach. That beautiful beach is kind of an artificial beach created by a surfer's paradise. Surfer's paradise has been created, not naturally been there. Maybe she will give some input to you. So, many things is all our engineering morals, and see, if we play around very intelligently, we can win. It is not that we are winning against nature. We have to always work with the nature to get best for the humans. So, that is one of the very important thing. If we kick back, then environment also will kick back. So, that is what one of the very important subject is coastal engineering, in the sense that it is a very sensitive, very complex, etc. And in any vertical, either the numerical modeling or physical modeling in the laboratory, model scale down, or in the field, in all three verticals very complex, quite complex. Lot of uncertainty, lot of unpredictable, etc. either in terms of the approximation in the numerical model, in the laboratory model scale down itself quite challenge. Most of the time we cannot work with the geometrically similar model for the coastal engineering. And field, how to measure a particular parameter, so how to measure a sediment transport, still it is a very much open question, or there are a lot of question. If I do, you can make a question, and if you do, I will always make a question that your measurement is not correct. That means a lot of uncertainty, and most of the time qualitatively if you assess, that is the best measurement, always we do it in the coastal engineering in the field. So, in this sense, in all three vertical there are a lot of open questions are there. That means for the researchers, lot of open research questions that can be solved, but those who are for the field applications, you should aware how are you going to play the game, which is very important. It is not that just 3 plus 2 is equal to 5, we cannot make a simple statement in the coastal engineering. It will give 5 at one place, another place it will give 6, another place it will give -5. So, because if we know the trick, then always we can make it. So, that is what always I used to say, for the coastal engineering is a very, very tricky subject. So, knowing the fundamentals and also with the field experience, both are very, very important to kick start a ball in the coastal engineering. So, keep that in mind, and many of you have done the course overview and objectives, and this is the coastal processes modeling, and I will give you a very brief kick start to the program, starting with what is the coastal processes with the and what we touch upon on very basics, and Professor Hong will continue with all the modeling, etc. for the, say for example, I will take 1 hour, then next nearly 10 hours over the next 3 days she will continue. Then we will conclude by lectures of field experiences, myself and my colleagues, and we will give it and close it by Friday. Saturday is only for those who are going to get the evaluation done. So, others is a Monday to Friday and 3 to 6. So, we will start 3 o'clock exactly at every day probably 6, maybe 6:15 or so, because definitely I know that you cannot sit for 3 hours, so we will make a break 15-20 minutes in between. So, that the break will be slightly plus or minus, depends on how the lectures are going. Okay. I hope the format is understandable for you. So, these are the course contents with the introduction. I am also going to give introduction. Professor Zhang also will continue for introduction, and then we will go for the numerical modeling in different perspectives. I will tell the basic numerical modeling background as I will make the quote ready for game. She will continue. Finally, we conclude with the case studies with what is our experiences. Case studies predominantly, if you go for that, it comes in 2 aspects. One is predominantly it goes for the developments like a port and many industry activities along the coast. Second major part is the coastal protection, and we disturb the coast in the first part in terms of the industrial development, including the port. Then it kicks back to us, then we go for again coastal protection, again a kind of a disturbance we are making to the entire system. Actually, it's we cannot come out of this loop once we enter into it. And as an engineering perspective, always I tell, and development is inevitable. We cannot stop doing the development because it's going to get kicked back to us. So, development is inevitable. We have to work for the balance, for the total system balance we have to make it, keeping the developments alive. So, if you keep our hands tight, at the end of the day, nothing, no developments. So, definitely developments are there. Definitely we are going into the field, and field will kick back. Again we are going for protection. Again it will kick back, and finally we have to make a conclusion part, how we will make a win-win situation for everyone. So, that's what last 3 to 4 hours of lectures are concentrated on the case studies on the coastal engineering, and Professor Zhang also will give in between on the her experiences with the other places. So, this at rough guidelines, and there will be some overlap between hours, etc. Already it is shared with you, all of you, and today and tomorrow Professor Zhang will continue with that waves, then sediment transport, and then advanced modeling. And she will also mention to you, she also some plan, if you all of you have laptop, she can give some modules, algorithms to run on it. Probably she will give more input. If you do not have, does not matter, you share with your friends or something today, or later you can take it. Okay. So, evaluation is for a Saturday, but we will work out later. Yes, if you are only alone, we will try to see how best we can do it. Okay. Now, and the entire program is concentrated as engineering background. Okay. I am making it very explicit, because once we talk about the coastal processes, and it can be seen from geological perspective, ocean science perspective, and coastal engineering perspective. We are looking at from the coastal engineering perspective, not on the geological perspective, not on the ocean scientist. Okay, you are clear. So, I am trying to see engineering developments along the coast. I am looking at the coastal processes in that angle. In overall, in simple manner, in any of the vertical, geologist or science or engineering or any other perspective, coastal process is nothing but how a sediment is moving from one point to another point in a very simple one line statement. So, this is that coastal process, which makes the coastal morphological have substantial changes over the years, or over the decades, or over the centuries, or over the millennium years. So, from the geological perspective, they will be more worried about in terms of the thousands of years, if not more. But engineering, all our system design, we are doing it for 50 years or 100 years cycle, our design life of the structures. So, our all concentration will be what happened to the coastal morphology in the circle. What is my immediate impact? Immediate means in some month or year or over the years. My design of structure is for 50 years. what would happen to the my coastal morphology in the vicinity of my coastal structure or the jetty, berthing jetty, what will happen? I am more interested in 50 years what will happen. So, my perspectives are much in a shorter framework in terms of the time frame compared to others. So, that is what I told you we are looking at from the engineering perspective. So, and this once we start off thing geological perspective, starting from weathering and erosion in the sense of the how the rock is getting slowly getting eroded over the wind, say for example, or the continuous impact of the water or waves, and then how it is been degrading into a finer particle then transport. Now straight away we are going for a transport directly. I do not have a time for thousands of years for rock to degrade. Okay. So, we are saying if it is a rocky coast, then we will go for the further engineering development. If it is a sand is sand, silt is silt, clay is clay. So, we are taking it by default the coastal morphology from geological scale we are freezing it and we are going for the further down. Now, ultimately I am boiling down to that how the shape of the coastline or the other side, how my livelihood, say either the fisherman community, those are one of the major stakeholder of the coast, how they are effectively utilizing the coast, for that what is their requirement. Second, and it is evident that entire world coast is continuously been changing, not only due to the regular ambient environmental forces, but so for climate change we are talking about it, and India climate change we are visibly seeing it, say cyclones more once in a year, once in one cyclone in Bay of Bengal becomes minimum 2 in a Bay of Bengal, once in 5 years in Arabian Sea makes every year at the Arabian Sea, and also subsequent cyclones in the same coast make a irreversible loss. Earlier cyclone hits a particular coast, the loss is immediately recovered within a next few weeks, not even months, but nowadays we are paying a permanent loss of the coastline. These are the evident changes that we are seeing from the climate change angle also. So, sea level rise is over and above that. So, these are the evident changes that makes a many coast across the world is not in a equilibrium stage, and at least for definitely I am 100% saying that in engineering scale none of the coast is equilibrium. So, for any developments also we have to be very careful in planning and other places. Now, and under coastal processes if I divide, and main part you will see this is the major part, erosion and weathering, that means degrading into small particles first of all, then transportation, then deposition. So, deposition also I can make it the last sentence erosion come deposition, because erosion is again repeated. Now, the word erosion for us is sediment transport, not the one what you typically see in the coastal process where erosion is the degradation of the larger rock into smaller fragments. And entire system what we are worrying about is last two, transportation and deposition and erosion. In the these are the coastal processes that we are going to discuss about it. While we talk about from the engineering sense perspective, either it is a too much sediment or too less sediment, or sediment starved coast or sediment surplus coast, both has its own pros and cons. I cannot say sediment deposition is always good. So, always all of you have in mind that sediment erosion is not good, but I can also say sediment deposition also not good, because the sediment deposition along the river mouth makes the flow across the river much less. So, all of you know who are coming from Chennai, Kuvam, because of the river mouth closure entire river got clogged, now it is kind of a only sewage. So, this has happened over the many decades, now we are trying to revamp it. So, then sediment deposition in the harbour makes a dredging cost exorbitantly very high. So, it is not only the sediment erosion, sediment deposition also be a very important thing, and needless to say sediment erosion all of you are aware that beach loss is one of the things everyone we are working for against the erosion. Next, these are the important part, and there are four important parts. One is morphology, and second material, third the driving forces, and ultimately any human activities in the system, either in terms of the industry development or major ports or minor fishing harbour, and or even coastal protection also be an intervention to the coast. All these things make a coastal process to be different than the so called the equilibrium coast. So, we will be concentrating more on the driving forces, and due to the anthropogenic activity how it is going to be varying the coastal process. This is the ultimate aim of this course. For that, definitely material is a very, very important part. Material, whether it is a coarse sand to the clay, which makes lot of substantial changes for a given ambient for driving force too. So, of course, vegetation is definitely a good system of protection of the coast, but there are a lot of questionable, wherever we are making a development, we are not ready to dedicate say 200 meter width of the coast to be a vegetation, definitely. So, wherever we need development, we are not ready to go for the vegetation as a good solution environmentally or naturally working with the system. And all of the things we are working with a given land form, we are not waiting for a geological scale to happen, because I am interested only in 50 years to 100 years of my life cycle. So, I will touch upon briefly on the driving forces, and same thing speaker also Professor Shang also will continue, and then sediment transport, because these two are the major important modeling perspective you are going to learn in the total 15 hours. Okay. Now, what are we dealing with? If we see the frequency of the forces versus the energy, and if you look at it, and this chart gives the higher one gives the higher energy. X axis is your in terms of the frequency or the time scale. So, in terms of the time scale or the frequency, left part is a low frequency, high frequencies on the right side, or in terms of the wave period, if I say highest energy content is in the so called ocean waves, or the what we call is a wind waves or simply waves. The sense that what you are looking at the waves at the open ocean is the one going to make lot of driving the sediment from one point to another point, because where entire energy content is there. That is one of the reasons that most of our sediment transport, one of the major driving force is the ocean waves, which is the wind induced waves, 5 to 15 seconds or 5 to 20 seconds of that range. So, another important component where like a narrow regions like a Gulf or like in Sundarban India, all places the current also be a dominant thing in addition to rivers etc., and current is again generated by the wind induced waves, but that current intensity is much less in the open ocean. However, when there is a tide induced current is there, wave induced current will play a aggravated effect to a particular coast. So, tide has a 12 hours and 24 hours in this particular region tide. Now, this is a wind wave and this is a tidal one. These two are every day, or tide is a every minute action, every second action in a particular coast or any places. But in the open coast, its influence is much less. Sediment transport due to the tide in an open coast will be much less, unless it is been aggravated. If we construct a breakwater, then the current pattern will also get changed. Tide might influence in hands on with the wind waves. Otherwise, tidal influence can be greatly ignored in the open coast without any protrusion. So, then in between up to 20 minutes to 2 hours is a tsunami and siege, that is a harbor oscillation, all those things comes under the long wave component. Much smaller than say for example, the less than 1 or 2 second wave, most of the time that will not influence anything on the sediment transport. As far as this program is concerned, we need not be worried about much on this part. So, we can broadly divide into right hand side is be a short wave, left hand side is a long wave. That means harbor oscillations to wind waves will be coming at the short wave modeling, and tsunami to the tide will be the long wave modeling. Which is very important because the mathematical basis on which we start itself a totally different framework for short wave and the long wave modeling. Long wave modeling also we can formulate many things. Let us say for example cyclone surge, storm surge, we can also do with the long wave modeling, and also with the short wave modeling we have some of the things what we predict ultimately in the fluid mechanics UVWP and in different forms. But while we predict a short wave, I am going to predict the energy advection from one point to another point. That is one of the very important thing. How much wave energy is going from one point to another point in the deeper waters. When coming to the near shore, I am also interested how the wave crest is bending to a particular coastline, so that whether it is going to be a concentration due to refraction, shoaling and diffraction, all those processes are very important. So there are two set of modeling, phase averaging, phase resolving. So that is comes under the short wave. Coming to the long wave hydrodynamics, without the hydrodynamics we cannot add to a morphology, coastal morphology, which is very important to accommodate the sediment transport in the near shore region also. So a combination of these two vertical modelings, long wave modeling and short wave modeling, is essential for next step of adding a sediment transport modeling to this picture. And sediment transport model is kind of even now it is empirical. Okay. We have sound physics behind it, how we develop the model, but still I can say most of the time we are going to bat with the empirical coefficients, or a coefficient is tuned in from the field measured or laboratory measured part. So all sediment transport models are driven by either the short wave model or long wave model or both together. Nowadays we are always using the radiation stress from one component to another component, so that we get a realistic sediment transport model. So that is for the first on the driving force, and second part you will be seeing a sediment transport model, and combinedly it will become ultimately we can predict the entire coastal process. Quick on that, if we talk about the wave deformation, which are very important, because near shore in the open ocean where the case is different. In the near shore there are many processes, near shore processes, refraction, shoaling, diffraction, and one important thing is the dissipation of the energy, that is a wave breaking, and which induces, it transfers the entire energy or momentum to the entire water column, which is because energy cannot be created or destroyed, the released energy works to lift the sediment or transport the sediment from one point to another point. That is what the wave breaking is, one of the very important part in entire process of the coastal processes. Then reflection, if any structure or the coast, if the reflection is more, that will be add on to the entire system. Then to the wave current interaction, this current is it can be open ocean current or tide induced current. Most of the time tide induced current with wind waves make a enormous impact into the entire system. So little bit on the wave dynamics, shoaling makes increase of the wave height, and how many of you are background with wave dynamics? Okay, many. How many of you don't have anything, don't know anything on waves? Anyone? Waves, ocean waves. You don't have any background. Okay. So it will be difficult, little bit difficult, because most of the time we assume fundamentals on the ocean waves and fundamentals on the ocean tide should be known to you. This is very difficult. Okay. This is just maybe probably you can talk to some of IIT students. Please refer to him about NPTEL lecture notes. Okay, wave dynamics, and they will tell you. Just go through tonight and tomorrow night, so that freshen up. Okay. And refraction and diffraction, it is having some kind of commonality in terms of the thing, it changing the wave direction due to refraction is due to the variation in the bottom topography, and diffraction is due to the projected protruding structures, and refraction changes the wave direction and same thing is done in the wave diffraction also. It is called the lateral transfer of energy, which is nothing but again the waves are changing the wave direction. And wave breaking, and many of you are familiar with that because that is one of the things always attract when we go to the beach and watch on the wave breaking. Is one of the good fun spending time and also relaxing mind. Now, and one of the very important that you should know, even we are stressed always, that the ocean waves does not transfer the energy, a mass. If we throw open a ball in the open ocean beyond the point of breaking, the ball literally or theoretically it will stay on its own, because you are throwing very near the shore, slowly it will drift and come up to the shoreline. But in the open ocean, in the deep water 1000 meter water depth, if you throw literally it will stay at the same point and under the action of the waves. So, that means waves will not transfer the mass, it will transfer the energy from one point to another point. That is what the wave modeling also, ocean wave modeling also, it is called the energy transport equation we use. But the other side, long wave, particularly hydrodynamic modeling, it is not the energy transport. That is a fundamental difference between the core aspect of the modeling itself. And quick aspect, in the deep water, the water particle velocity is at the circular orbit, it will die down at a distance which is equal to the half the wavelength. So, that means the waves will not be felt by the seabed itself. So, the energy will be dissipate or it will be slowly die down with hyperbolic variation, and at the wavelength of L by 2, if the 100 meter is wave, that is about 8-second wave, is 100 meter is wavelength, 50 meter depth, below 50 meter depth, if the seabed is there, it will never feel, seabed will never feel that there is a wave action. But if the seabed is much shallower, 20 meter, then this particle will get interfere, then what will happen is slowly the circular orbit becomes an elliptical orbit. So, this will happen slowly to the near shore, where the very shallow water or water particle velocity will be elliptical, in the sense that the horizontal water particle velocity from the free surface to the seabed will be almost of the same magnitude, while the vertical water particle velocity will die down drastically from free surface to the seabed. That means the seabed will get influenced or driven by the ocean wave. There will be this water particle velocity will make a sediment will drift to one point to another point. So, that is one of the very reason that we divided into deep water waves to the shallow water waves, which is also important for in terms of the moving the sediment. And when this water particle is getting influenced by the seabed, that means the seabed will alter the waveform. That is what, there are two main processes called the refraction and shoaling. And the shoaling, it will try to align the wave crest parallel to the bathymetry. Ultimately, at the end of the thing, consistently if the same direction is there, it tries to align the wave crest will become parallel to the shoreline, parallel to the seabed contour. So, that is what most of the time always you look at it, the open ocean, particularly during non-monsoon time, always waves will come towards perpendicular to the or parallel to the shoreline, or directly it will reaches directly, because always the most of the time near shore seabed contours are parallel to the shoreline, and this process is called the refraction. And in the shoaling, and particularly this is that refraction, this is for whenever there is headland, because the seabed contours, the white line is a seabed contours, and it will make a wave direction changes such that always it makes a headland concentration towards the headlands. Whenever there is a bay, there will be a divergence. This is another reason, wherever there is a bay, always you see a beach, because of the divergence, energy will get dispersed over a wider medium, sediment will get deposited. However, this headland erosion will be there, but most of the time headlands will get an equilibrium shape, in the sense that if there is a rocky coast, rocks will resist that wave force. So, that is what headlands will always exist only when there will be a the strong base is a kind of a rock. So, the headland and thing. Next, in this bottom, another shoaling, which is the increase of the wave height. Next slide I will show you, but these two makes the entire wave properties to be different, either in terms of the waveform. A pure sine or cosine wave takes into a very long trough to the very short crest. That is one waveform changes. Another waveform, the celerity very near to the coast, the wave celerity is not depends on the wave height and wave period, wave characteristic itself. It depends on only on the water depth. Water depth dictates what is the speed of the wave, which is a very important things which makes the seabed drives the system. Shoaling is increase of the wave height. A normal wave, say for example about 50 centimeter wave towards the coast, it will bring into 1 meter or 2 meter, finally it breaks. Ultimately it is a waveform is all are the water particle mass. It cannot stand or pile up beyond certain extent. So, it has its own limitations. So, it will break after certain depth, it is called the wave breaking. This is purely based on the shoaling. Now, wave breaking, and we can classify predominantly of 4 types: spilling, plunging, collapsing and surging. And spilling, most of the time we talk about in the deep sea or water depth is sufficient, finite water depth or deep water depth, and plunging always that you see what you call this surface paradise. If we talk about it, that means we look at the plunging, where surfers love to surf on across the plunging. Then surging and collapsing are at the coastline most of the time. Just a snapshot of different systems, and the so called plunging is one of the powerful system where the energy loss due to plunging is enormous. So, obviously when there is energy loss, that energy will work with the sediment for its transport. So, that is what the surf, if you talk about itself a plunging wave, which is a powerful erosive agent at the particular area. It lifts off all the sediment material, then the current induced by both wave and add upon with tide will drift the sediments lifted by the plunging wave to the next location. It is not get supplemented by the from the another direction, then always it will be a depriving course to the particular area where the wave is breaking. And coming to the ocean current, these are on the waves. It is a very broad classification, because I want to just clips apart the thing. Open ocean currents can be induced by density distribution, which is we are not at all going to talk about it. Okay. So, water free surface, say in 1000 meter water depth, and water at bottom may be much more dense compared to the free surface. This will be most of the time it will be true, particularly for the tropical waters. Tropical waters temperature is high at the free surface, and also compared to the bottom, your density is also function of your temperature and salinity. So, if the temperature is low, which is true in the bottom, and also salinity is very high, you are going to get a high dense water compared to the free surface, particularly in the tropical water, easy to explain compared to the subtropical water and other places, and it will be there will be a lot of mix of between temperature and salinity distribution, and this makes a low dense water above the high dense water, and this density distribution also make a exchange of the water particle across the water column, which is called the water current due to the density distribution. And then tidal current is very important in the sense that, and every minute, every second it is occurring over the entire thing. Tide is due to the attraction between the celestial bodies, okay, sun, moon and earth. So, it always exists at any point of the places. Wherever there are some constraint, particularly in India, Bay of Bengal and Arabian Sea, even I can make it, there will be a kind of a funnel shaped on both ends. So, water is pushing towards northern parts, always our tidal range is very high compared to the southern parts. So, Tamil Nadu is on the southern part. So, here it starts about 1 meter, 1.2 meter, and Chennai is 1.2 meter. If you go to the Vizag, and then it will be a 1.5, 1.6. Orissa, it becomes a 3.5. West Bengal, then it exceeds a 5 meter. So, it is a funnel shaped, what is pushing there. Then one higher the tidal range, higher the tide induced current also. And then currents caused by the surface waves, which is of very important for the sediment transport, because the along shore current, cross shore current induced by the waves are the one going to make a sediment drift from one point to another point. So, the source is the sediment. There are two places, one how it is getting lifted up, how it is being transferred, this is one, and the last one is currents caused by wind. That is what I call the open ocean current induced by wind itself. Waves also induced by the wind. So, this open ocean current is normally very less. See, even in the Bay of Bengal, open ocean current induced by wind will be 5 centimeter to 20 centimeter per second. So, very small compared to the other places, but it maybe needs to be taken into account over and above the other places if other currents are also being vulnerable. And many other classification etc., it is just for your information, but which is very important for sediment transport due to waves are again the shallow water. I am interested because sediment transport in the near shore region is very important, where there will be a current makes the mass transport, and when the ball is drifting free surface, that means there is a mass transport in the wave propagation itself. Then along shore current, that means current moving along the shoreline, and onshore offshore or cross shore, second one, it is also called the cross shore, where the current particle moving perpendicular to the coastline. Then the one important part is rip current. Rip current is the one, many of the places even India nowadays very commonly they are keeping it, particularly Goa mandatory they are doing it, Australia they have been doing it long time, and some places they will keep a red flag. Morning they will keep it on one place, another place in the afternoon and evening they will keep on moving that. That means there is a rip current. Rip current is the one current pushing towards the deep waters, where if you caught in the rip current, one of the easy ways to escape is do nothing and it will throw us in the water depth of say 1.5 meter or so, then we can relaxedly come back crossing it. If you work against rip current, all our energy will be lost, then there will be a catastrophic impact will come on the humans. So, that is a rip current is one of the dangerous one, which can be easily predictable for a particular coastal morphology. That is what we are keeping a red flag at beaches. Just to have an idea, in the ocean current, what is that intensity? Open ocean current very less, up to 30 meter per second. Say you can roughly take 1 knot is equal to half meter per second, okay, 0.5, you just multiply by half, just a quick conversion. And initial currents are very small, but if you look at the tidal current, say even in Gulf of Kutch and Gulf of Kambat, it easily an average tidal induced current goes up to 2 meter per second casually, but it can also reach about 2.75 meter per second also many places we could able to record. This is a everyday event. Of course, wave induced current is small, but our most of the interest is to get the sediment transport due to the wave induced, so which will add up with the tidal induced current makes a catastrophic effect on sediment drifting. So, ultimately waves transport energy, current transport mass transport, and tide is a simple long wave, whereas tide you can make it both potential energy form and kinetic energy form, the way in which we look at it. Now, these are all our driving forces, a quick glimpse of the driving forces, and Professor Zhang will take for the modeling also by giving today continue on the more given on introduction. On sediment transport, there are two main important aspects, and the gravity always make sure that a sediment is retained. However, the driving forces that we discussed now and makes the systems to move. So, the sediment transport always we do it two aspects. A minimum, what is the minimum energy required to lift a sediment up? Till that time sediment will not move, even sufficient current is also there. So, a sediment has to be lifted up, then current will do its job for drifting from one point to another point. So, then drifting also, one is on the bed itself, many of you know what is a boundary layer theory. Now, sediment transport, our boundary layer thickness is much more larger, more than the fluid mechanics. So, that is a bed load. Then those car coming to that water column, most of the time the balance of the by energy retained by in the water column by the waves or other driving forces to the gravity, if it retains a long time, then it will get drifted away for longer distance. If it is a heavy particle, it will not get drifted away unless the force, driving force magnitude is much higher. So, always it is easy for in engineering perspective to calculate. However, the question is that what is the bond between one particle to another particle, everything has been approximated in many theoretical sense. That is one of the important challenges that always we do it. So, in the shield stress, Shield's parameter, very popularly known Shield's parameter, makes the, or the parameter is defined, makes the balance of the both, how the, whether the sediment is going to lifted up or not, it is a threshold value. So, more on equation part etc., we will see it later. A simple graph which directly borrowed from the internet is the diameter of grain size or the sediment size to the average flow velocity. Average flow velocity either from waves or the tide induced current, both either way we can take it, and larger the size of the sediment, that means gravity is acting on it, that means it is making a deposition, and flow velocity is larger means driving force intensity is very large. So, if you look at it and it makes a maximum erosion at an optimum value, and say minor particle also will not get lifted up because every particle needs some kind of a threshold value of flow velocity to get lifted. Say for example 0.001 mm velocity, particle size also requires a kind of a flow velocity to make it happen. So, then only the erosion comes. Okay. So, the shield stress and shields media, of course, very series of laboratory tests and also supplemented, later supplemented by many authors by the field measurements. Well, still it is popularly called the Shield's parameter, and also the stress calculated it also based on that, and of course all based on the Reynolds stress, because particularly the turbulence. And this is empirical relation, definitely it is empirical relation. Of course, all are looking beautifully like a physics based equation, but there is no other choice, we have to only follow only this kind of the equations, and these are the best estimator that is available as on today. So, this is the Shield's parameter. So, popularly with reference to the ratio between the stress, that is the driving force in the numerator, denominator is nothing but our, that is a rho of particle minus rho of fluid is nothing but we are deducting the buoyancy force. Okay, buoyant effect also taken into account, and also the weight. So, denominator is nothing but the net weight of the particle at the in the submerged state, and the numerator is nothing but the force. So, it is a simple equation, actually that is why in terms of the simple physics it is a physics based observation, but the parameter value, the arbitrary value, we can always debate this parameter is, and this value is enough, or this value is not enough for erosion or deposition etc., that is always a debatable and across a different problem. So, if we plot it Reynolds to the Shield's parameter, again we can make the region of where no transport, there will not be any transport, then I already mentioned to you suspension and the bed load. Sediment transport that can occur along the bed, rolling of the sediment along the seabed itself, or once it is coming to the suspension load, the movement will be much or one order higher than the bed load transport. So, all these things are possible. So, maybe more things in later in some of the things. So, there are two predominant one, because the modeling itself, bed transport model and suspended transport model, there are two different models are there. That is what I am highlighting to you, and because the bed load transport, the process is different, and suspended load transport is just moving from advection, a fluid particle velocity and to the sediment. it plays simply on that. But when it is bed load, friction between one particle to another particle also plays a major role in moving the system. So, that is what the two bed load transport model cannot be worked for the suspended load and also the vice versa. So, I will not go much details about more detailing about it. So maybe on Wednesday Professor Zhang will continue on most of the bed load transport as well as also the suspender load part, and I will just highlight it. There are so many empirical, or some of them they call the semi empirical relations between the for the bed load transport compared to the suspended load transport. Bed load transport equations are much more because of its complexity, much more, because always suspended load also it has to cross that the so called the sediment boundary layer and has to come out, but once come out then it will be just affected. So, once it is always in the suspension, easy to model compared to a bed load. So, that is what many of the bed load transport models are very unique. Now, just few things. Now, knowing that what is your driving force, what is the sediment transport, or how the sediment is moving, and a short wave with high energy. And the thing is that short wave with high energy, one energy is always expressed in terms of the wave height, correct? Energy is a h square, energy is a h square, and a short wave always makes the shoaling effect, and always it goes up to the breaking. Breaking also makes a lot of energy loss in or energy release into the system. So, which means it can advect lot of sediment into the system. But most of the time the long wave, when it is a long wave, the amplitude is much less relative to the wavelength, all are relative sets, and but which makes slowly it will drift this sediment bar drift towards the coastline, and this process I can put it in the other word in terms of the more specific to Indian coast is that monsoon waves, I can put it the first classification top, and non-monsoon waves at the bottom. And always during the at the end of the monsoon, most of the eroded coast will get supplemented with the sediment because of this action of the so called, that is what the winter is the monsoon and the summer is the non-monsoon waves. Non-monsoon waves are always work for replenishing the particular coastline, and typically this is a typical state that we can see at many locations across in India. Kerala coast, it is a very common sight. There will be a steep cut during monsoon, and no wonder within the next few weeks of end of the monsoon we will get a very good beach back. Okay. So, the steep cut is due to so called the onshore offshore sediment transport. And coming to that very claims of it with the numeric modeling brief, I will stop on that. And of course, all models are properly comes or derived from the continuity equation, Navier-Stokes equation, and the Bernoulli, that is energy equation. And broadly if I categorize into the wave models, one is on the deep water, another is a near shore, and the shallow water wave equations in full form in 3D or in two dimensional form. Most of the shallow water wave equations we are writing it in terms of the two dimensional form. That means either it is a vertically integrated or some approximation on the distribution on the third direction, that is all are xy plane, that is a horizontal plane. Most of the things are that is a two dimensional. And the wave prediction itself, because ocean wave, that is what so called the short waves, and we need to predict shoaling, refraction, and if there is a diffraction then all the more a little more complex. And there are two aspects. What we call is the one is a phase averaging model and another is a phase resolving models. And phase averaging model is we are more interested in the energy transport from one point to another point, where the influence of the bottom is much less, or even if the influence is much more, we required in terms of the average energy concentration, that means average of one wavelength at least. So, that is what on the right hand side it is called the phase averaging model. I model only the spectrum, not in the wave crest itself. Wave crest and wave trough I will not capture in the phase averaging model, only the energy. Most of the time even near shore it is more than sufficient, but there is only the hint is that the spectrum cannot be drawn for a waves with less than the wavelength grid. So, but we can see nowadays even for the some published paper, phase averaging model, wave spectrum model, they apply for even 20 meter grid, which is not at all correct, which is cannot be predictable. And but phase resolving or the phase capturing model, it will capture how the wave is going to refract, how the wave is going to diffract around the breakwater, how it is changing its direction, how the lateral transfer of the energy is going to happen, how the wave crest is going to concentrate with the two breakwater. Both the breakwater, if it diffract at some particular location, it will get converge also. So, the convergence points are not good points. So, either in terms of sediment transport, even for other functional aspect, we cannot place a or berth a ship where the convergence is happening. All those things are also very important. That can be only predicted by the phase resolving model, which cannot be predicted by the phase averaging models. So, there are very clear distinction. Being at the near shore, both are very important for us. I will not say that phase resolving model alone is enough for us, because many times phase averaging model also will be very handy tool for us to get the energy distribution across the entire domain. So, you should know both. Next, coming to the morphodynamic model, and there are broadly I can make a static dynamic, two categories, and the so called the Bruns model or the Bruns rule are very commonly been adopted. Because Bruns rule with so much modification changes in the over the years, and it can be applied provided you understand the each and every parameter of the Bruns rule. And only the drawback of the system is that because of the static model, a rise in the water level, they call the sea level rise, but that sea level rise is not the one sea level rise due to the climate change. Okay. So, even it can be taken in a different sense, and but there will be an arbitrary rise of the sea level. What is the equilibrium at the next stage? This is what they do it in the Bruns model, but most of the time that is not sufficient for us, because later Edelman and Dean, so many of them, they develop a model. Even now we are very happy with that model, because sometimes with lot of struggle with all dynamic models, at the end of the day we will not get much better than the static model. So, that is what even the static models also been much popular in all the directions. Now, dynamic models comes into the place. We run the wave model, we run the hydrodynamic model, get all the driving forces in terms of the particle velocity or in terms of the radiation stress, then add over and above add the bed load transport model, then suspended load by default we can use advection, and all those, that is a sediment transport modules, and over and about finally end up with the final coastal morphology we can predict on the dynamic model, which is a systematic from the first to the end. So, there are so many models, S-beach, and commercial models are also there for many aspects, which makes the either take the static into aspect or full dynamic also. Dynamic means you have to make a systematic applications. Okay. So, this is what static model will do. When there is a change in the water level at an equilibrium stage, that is always do that. If there is a change in water level and stays for sufficient time, I will not make a definition of the time now, sufficient time, that means it will get erode this part and it will get deposit at the bottom part. So, there will be a always they make an equilibrium sediment erosion near shore or the at the shoreline to the sediment deposition and to the, I will not say deeper water, because deeper water in wave dynamics way it is different, but in morphological thing it is a deeper water will deposit. Always the equilibrium of the sediment is retained, but no longer it is not going to work, because most of the time it is not only happening along the beach profile, there will be a advection of the sediment along the perpendicular to this cross section. How to make a balance, that will be one of the very important part, but this is always true when a cyclone hit or a very severe monsoon hit. Bruns model, a static model will do a very better prediction. perfectly it will also predict the things. So, even though there is a along shore movement of the sediment and cross shore movement of sediment, very close relation, unfortunately even today along shore transport models are separate, sediment transport models are separate, cross shore sediment transport models are separate. There is no link between these two, even though we are working towards a more dynamic models making it here happen. And dynamic, which is also called the bottom up models, integrate the full driving force models, short wave or long wave, with the sediment transport models, with all so many sediment transport equation etc. integrate in very good form, linked to a particle velocities, and we can drive it with 3 stages: hydrodynamic, which includes waves and long wave and short wave, then sediment dynamic submodule, which estimates the sediment transport due to the waves and also to the current. Okay. Most of the time nowadays either the wave over the current or current over the waves, either way how we take the radiation stress from first form, add a radiation stress from the second part, it depends on your expertise that you can make it. Finally, the morphological module, separate module, that we can add it to the first 2 modules to make a new morphology or to predict the new coastal morphology into the entire system. This is the entire modeling into the system. And this wave and current combination, always you have to look at it. When current is much less, does not matter, but when current has some magnitude, which is very important. Okay. Okay. Now, I think I will not go much on the morphological module, because again we can make a kind of empirical to, or this morphological model, the so called this profile, say initial profile is a dotted line, final profile is a continuous line. This profile is kind of only fitting line. It is actually a fitting line, in the sense that they will assume this shape of the original profile and the shape of the final profile remains same with some twist or with a horizontal drift etc. Actually, there is just an assumption that is made. That means that is not at all true for any coast. That is what hundreds of authors has replicated the same static model with different profiles, because applicable to, say I can make a one for Chennai coast, another for Nagapattinam coast, another for Nellore coast, we can make it. So, that means the fitting equation is not same. If you arbitrarily take one author, then it will not fit into our coastline. So, that means, but even if we want to do our coastline, we need an enormous amount of data for our particular coastal stretch, which is also not at all possible to get it at all the coastline. So, while you are taking a particularly the static models, you have to be very careful about this, what is the thing they have made a so called the fitting. The last lecture on Friday, so we address it with a proper measurement at the field, Mahabalipuram site, how we made a systematic sediment transport. If you try to fit it, what are the complications, we arouse it, we will explain to you. Okay. And finally, on the Bosenic model, I am not sure whether Professor Zhang is covering or not, but Bosenic model is another comprehensive model, but because of that it's a complex system and combination of the so called the short wave, long wave, and either we can tune on either side. I can work for short waves with the Bosenic model, I can work with the long wave with the Bosenic model, and those who are working with the long wave, they never bother about short wave parts, same thing the vice versa. All those things, Bosenic model is very complex and it takes care of the wave breaking, many aspects that cannot be taken by most of the phase resolving models in a full form, and we can tune the Bosenic model for wave breaking. That means we can add on the morphological module, easily fit into a Bosenic model and to drive the sediment transport. So, that is one of the advantages of it, and many of the recent commercial packages, they also have the Bosenic modeling system also there, but how we are going to integrate into the entire system is very important. So, the all suspended load, bed load etc. already mentioned to you. Same thing is for every other location also it is there, that we can comprehensively make it to a Bosenic called morphological module, but morphological module is a standalone which you can fit into any other locations. Okay. So, any other system where that you can make it. Ultimately, if you want to have a very comprehensive look at it, a full dynamic module, you have to integrate your offshore wave to the nearshore wave and hydrodynamics, and for the material is with you. Initial morphology is given to you, what is the material is there given to you with both waves, and you are driving the sediment transport. Most of the time it is been work about sediment transport, it been work on or build the modules on the hydrodynamics module. That is what the short wave, the so called the short wave input is given to the hydrodynamic model. Even the influence of the short wave is much large, okay, because what is the more important is that the entire system we need a particle velocity, so which is easily given by the hydrodynamic modules. So this is my last slide, and either in terms of the dredging or depositing the or artificial dumping, that means see we are doing maintenance dredging for all our ports, major ports, we are dumping in the offshore again. All these are either the source or sink, and sediments from the rivers are the continuous suppliers, but either in terms of the dams or short dikes we are preventing all the sediment movement into the ocean. That means we are making imbalance there itself. Then wind is also playing a major role most of the time. Wind, I have not talked about the wind induced sediment movement along the coastline is one of the very influencing factor for all sediment erosion or deposition. Then moving from one point to another point. Along shore always we see whether my shoreline is going to reduce or not, but that is also not important part, because how much sediment is going from say up to the subzone. Subzone is the one where it is a point of breaking, shoreline to subzone. So most of the time monsoon makes our seabed very steeper, that means sediment loss will be across a cross section, and which also moves the changes your shoreline, okay. So seabed change is also very important, not only on the shoreline. I think I will stop with that. So I will also end up with that complex system. None of the three vertical, numerical, laboratory or the physical or the field cannot give you a comprehensive single point solution. So you have to work with the balance of at least two, numerical and field, if not the laboratory. And of course in the over that last few decades it is understood that modeling a sediment itself a lot of challenges in the laboratory. So compared to the laboratory, the once upon a time few decades back, so many laboratory has been designed for the sediment transport models, but nowadays we are having much more better predictive tool. So we are going more towards this numerical modeling supplemented with the field measurements, okay. So I will stop with this one.